This will be our last chapter on Big Idea 2. As I've told you numerous times, you'll see a tremendous amount of Big Idea 2 testing come May the 7th when you take your AP exam. So we're still going to be focusing on the forces between molecules, and we're going to introduce a new type of force between molecules here, molecules in quotes, because you're going to be looking at the force between ions and polar covalent molecules such as water. A lot of what we do here is review from previous chapters, which will be excellent for your semester exam, which is right around the corner. Actually, it is 2 weeks from tomorrow. Properties of solutions. We know that solutions are formed when you dissolve solutes in solvents. And in the lab we did the other day, we were using isopropanol, which is a polar covalent molecule, and we used it of different concentrations. So for example, if you have 5% isopropanol, that is 5% alcohol and 95% water, and the solvent is the one present at higher concentration. So in this case, water is your solvent and the alcohol is your solute. We also use 70% isopropanol, which is rubbing alcohol, and that is going to be 70% alcohol and 30% water. So what would your solute be in this case?
Water.
Right. So just be careful with silly little things like this. And here the alcohol is the solvent. So the solute gets dissolved, the solvent does the dissolving. And there are many, many, many different ways that you can make solutions. There's actually 9 different possible combinations. We'll take a look at the 6 common types that you see here. And we talked about solutions last year. This should look familiar.
I know you said we're not going to have to do colligatives, but on the back of the periodic table last year, you know how they had all the solvents there? Are we going to have to use those or no?
No colligative properties assessed in AP Chem anymore, which is a shame because it's really fun. There's a lot of cool things you can do. You could link it back to complex stoichiometry, which I liked, and there's a really cool app. So, nope, they cut it out. Bye-bye. 6 common types of solution where you've got your solute, your solvent, and the state of the solution. And you'll see that the state of solution always matches the solvent. So whatever the solvent is what your solution is. So first of all, you can consider air, where you dissolve different gases, and the gas present at the highest concentration is nitrogen gas, so that would be your solvent, and the other substances such as oxygen, argon, CO2, and the other schmutz in air would be your solutes. Natural gases, for example, you can have ethane, you can have propane dissolved in methane. You can have gases dissolved in liquids. Some of you drink soda for breakfast. That is incredibly unhealthy. But you would have carbon dioxide gas dissolved in liquid water. Soda for breakfast is not the breakfast of champions. Please don't do that. My husband drinks soda for breakfast. It's disgusting. Blood substitutes, for example, oxygen dissolved in the liquid perfluorodecolon. I'm guessing this has 10 carbons. Kind of wonder what this looks like. We'll take a look at that afterward. Vinegar, 5% acetic acid dissolved in water. Vinegar is really good to get rid of smells and things. Good little trick. A lot of you wear contacts and you clean them with some type of saline. Sodium chloride in water. So look at your saline solutions, like for your contacts. Take a look at what's in there later. Racing fuel is naphthalene and gasoline. That I didn't know. Kind of cool. Solids dissolved in liquids is the most common type of solution that you tend to think about. When I make up most of your solutions, I go get some solid powder and I dissolve it in water, making an aqueous solution. But it's not the only type of solution you can make. You can have gases dissolved in solids. This is to light stoves with hydrogen and palladium. That's actually not that common. Solids dissolved in solids, we've seen this already with some of our alloys. 14 karat gold, silver dissolved in gold, so it's not pure gold per se. 24 karat is going to be more gold. And then brass, for example, zinc dissolved in copper, where you've seen that with your alloys previously. To represent concentration, the main way we do it is molarity. You have seen this last year, this year, etc. Moles of solute per total volume of solution in liters. At the AP level, we very often do millimoles of solute over mils of solution, especially when you have small volumes. It's just a little bit easier. You should be able to solve for that. I'm not concerned there. You know how to solve for concentrations of new solutions, or how to determine how to make new solutions using dilution. We talked about this earlier in the year. For example, if you have a 2 molar solution on your shelf of sodium chloride, that's your stock solution. That's what you're starting with. If you want to make 50 mils of half molar solution, how much stock is required? What would you do there? Without a calculator, you don't even have to write it out.
You would multiply the molarity of the stock at times like a variable, and then on the other side you have 50 milliliters times 0.50 molar, and then divide.
Yep. So you would have this times this divided by that, or you could even do it simpler, comparing 2 molar to half molar is a 4 times dilution, right? So 1/4 of this would be 12.5 mils of the stock, correct? And that's in a multiple choice situation, bam, done in less than 10 seconds, all right? How about this one? A chemist wants to make 100 mils of 0.75 molar mag chloride. What volume of a 1.5 mag chloride solution would he use? So what's the dilution there? A factor of 2. So that means that you need how much of this?
Oh, no, 50.
50 mils, because you wouldn't want to make more than you're asked to make. So 50 mils of this, and how much water to make 100 mils? 50. All right? This one also is very, very simple. It says, what is the concentration of chloride ion in a 0.750 molar calcium chloride solution? How do you formulate calcium chloride? CaCl2. So how many chloride ions per every 1 mole of calcium chloride?
2.
Right. So if you have calcium chloride, that's 1 calcium ion and 2 chloride ion for every 1 mole of this. So if this concentration is 0.750 molar, what's this concentration? Oh my. 1 to 2 mole ratio, so the concentration of chloride ion would be 1.50 molar? Is that what you said?
Yeah.
That's awesome. I thought you actually said 0.5. So you are correct. What would the concentration of calcium ion be? Same thing as this one. Easy peasy? And this is all review from chapter 4. Which was your favorite?
Reactions in H solutions.
Sure it is. That's kind of crooked. That's a little better. All right, you're good so far? Yes? Yes? Yes, yes? Okay. Other ways you can represent concentration. One is percent by mass. This you might see a little bit of. It's really very, very simple, percent by mass, where you have mass percent is the mass of the solute over the mass of solution. If they only give you the mass percent, you can assume that the mass of solution is 100 grams. That makes life easy. So it said storage batteries are 37.5% sulfuric acid by mass. If they want the mass of the solvent, you could do that very easily because you would know you have 37.5 grams of the acid over 100 grams of solution. So if you have 100 grams of solution and 37.5 grams of the acid, how could you figure out the mass of the water? You just subtract the two. And that's written out here. The other way you could do it, it says glucose is found in ripe grapes. What is the percent by mass of a solution made by dissolving 163 grams of glucose in 755 grams of water? So to get the mass of the solution, what would you do with those two? Add them. So you could do it that way. But I think you would be more apt to see something like that. The other one that's kind of interesting but not assessed anymore, I'll mention it because some of you are probably going to go into criminology and hopefully you will never encounter this piece in your life. But blood alcohol level is determined by percent by volume. Many of you are driving. Some of you unfortunately have started drinking, and I hope you never mix the two together. So blood alcohol levels is 0.08% by volume. That's 0.08 mils of ethanol, that's drinking alcohol, per 100 mils of blood. So in the event they ever want to do a blood alcohol level on somebody, they will draw some blood, let's say 1 mil, and they're going to look to see how many mils of ethanol you have per that mil of blood that they've drawn. So the legal limit for adults is 0.08%. I believe the legal limit for kids under 21 is much less. Make wise choices.
No, it can't be.
Make wise choices. I don't know what the percent is for kids your age, but we can look that up afterward. You're on it?
Yeah.
Let's look that up afterwards. So in regard to concentration of importance is molarity, percent by mass. Those are the two that you need to be comfortable with, especially molarity. In ACE Marine or ACE Environmental Management, which many of you are taking or have taken, it's half of it, right? So for kids under 21, that legal limit is half that amount, and that's all based on body weight. Be smart. You shouldn't be drinking anyway, and you certainly don't want to operate a car under the influence. We'll story tell later. Parts per million, parts per billion, nothing about me. I just have funny stories to tell you. Parts per million, parts per billion, parts per trillion.
Hilarious.
And you've probably seen that with ACE Environmental Management and ACE Marine, you've seen too. So those are other ways that you can express concentration. Mole fraction you've seen also. So moles of solute per moles of solution. We linked mole fraction to another variable in a chapter in the first 9 weeks. What was that chapter? It starts with a G. Gases. So we talked about the link between mole fraction and partial pressure, remember? This is all going to come back for the semester exam, right? Yeah, I know, it's so exciting.
I love semester exams.
I do. Mole fractions, be familiar there as well. You don't need molality anymore, they don't look at that. All right, what we also really want to introduce today are energetics of solution formation. Before we get into that hot and heavy, we want to make sure that you understand your IMFs that you were just assessed on. So we're going to look at the factors that affect solubility. And even last year you saw that likes dissolve likes. Nonpolar solutes tend to be soluble in nonpolar solvents, and polar solutes tend to be soluble in polar solvents. What we really want to focus on here is the why. So we're going to look at what happens when we add solutes to solvents. Our two solutes are going to be iodine and potassium permanganate. They're both purple solids. What do you know about iodine? It's a nonpolar covalent molecule, and its only type of IMF is LDFs. What do you know about potassium permanganate? It's ionic, right? It's ionic. It too is purple. Does it have LDFs? No. Does it have dipole to dipole? No. Can it hydrogen bond? No. All right. Let's take a look at two colorless immiscible liquids. What does immiscible mean? It can't mix together. IM means not. Miscible is mix. So these don't mix together. That is, if you do mix them, they will layer on top of one another. All right? They're both colorless. Water is what type of covalent molecule? Polar. It has LDFs, dipole to dipole, and it can form hydrogen bonds. Carbon tetrachloride is what type of molecule? Nonpolar covalent. It has dipoles that cancel due to the molecule's perfect symmetry. Good. All right. We're going to ask a series of questions here, and you'll want to pen some of this down. It says, what are the properties of each solute? All right. Iodine is, they're both purple. That's a physical property. Iodine's nonpolar covalent, NPC. IMFs, LDFs only.
Purple.
Why is it purple?
Because it reflects purple light.
Yeah, that's it. That's exactly right.
No, but like why?
Like what
Potassium's not
about?
purple and manganese isn't purple.
Permanganate ion is purple.
Okay.
It is. Permanganate ion's purple. Hence it's purple. All right. So this guy's purple. This is ionic. It has interionic interactions, right? Okay. Which is easier to separate intermolecularly, with that in quotes, because one of them's not molecular in nature. So what has stronger interforces, if you will? Definitely. This has stronger interforces, so the one that's easier to separate is going to be iodine with weaker IMFs, LDFs only. So it's going to take more energy, or in this case, which is easier to separate, it takes less energy to separate iodine because it only has weak LDFs. What are the properties of each solvent? Which solvent is nonpolar and why? So in regard to our solvents, they're both colorless. Water is a polar covalent molecule with LDFs, dippity-dippities, and hydrogen bonding capability. Carbon tetrachloride is a nonpolar covalent molecule. We talked about the why already. Its dipoles cancel due to the molecule being perfectly symmetrical. And so this has LDFs only. When you want to form a solution, it occurs in 3 steps, and this we'll hit in more detail next time. But to make a solution, you have solute. You must separate the solute, that is, break its intermolecular forces. You must separate or expand the solvent, that is, break its molecular forces, intermolecular forces. Breakage is endothermic. To form a solution, you must form IMFs between the solute and the solvent. And in order for a solution to form, the formation of those IMFs must be of greater strength, if you will, than the energy it took to break the IMFs in the solute and the solvent. And then you're looking at the formation between solute and solvent. Formation's going to be exothermic. So if that formation is more exothermic than the sum of the endothermic reactions, then the solution will form. And we'll look at that delta H concept next time. What happens when water and carbon tetrachloride are mixed? Which liquid is on top in a separatory funnel with the density of carbon tetrachloride provided? So when you mix them, they layer. Why would carbon tetrachloride be on the bottom? It's denser than water. Water has a density of about 1 gram per mil.
So would carbon tetrachloride be considered hydrophobic?
Yes. And we'll get into hydrophobicity and hydrophilicity next time. When iodine is added, in which phase will it dissolve and why? It's going to dissolve in the in this phase or this phase? And in which, you wanted to say layer?
Yeah.
Okay.
Carbon tetrachloride.
It's going to dissolve in this one because they're both nonpolar covalent, and the only force that can form between them is LDFs. All right? The other thing it might ask, how could you tell visually? How would you know it dissolved in that layer? The layer would turn purple. All right?
Never mind. Actually.
You're good?
Yeah.
When the experiment is repeated with potassium permanganate instead of iodine, in which layer will it dissolve and why? It's going to dissolve in the water, and this is the tricky part. This is the new piece of the puzzle. Most ionic substances are water soluble. In order for a substance to dissolve in water, you first must break those quote-unquote IMFs in the solute. In this case, with the ionic compound, you're breaking those inter-ionic interactions, which are strong. In order to expand the solvent, which is water in this case, you have to break LDFs, dipole to dipole, and hydrogen bonds. In order for the two to mix together now, you need to form some type of force that's stronger than everything you've just broken. And that new type of force is an ion-dipole interaction. And we're going to take a look at those. If you looked at these separatory funnels and carbon tetrachloride was on the bottom and water was on the top, which one would represent the potassium permanganate? The left one, because this layer turned purple, and that's why I said, what can you see visually? Here you would have iodine, and you can get cutesy little questions like this. If you were going to get a part 2 question in this chapter, it's going to be this cute little separatory funnel. It's adorable.
How would they show purple?
Are we gonna do that?
No, because we can't use organics in high school because you're not 18.
Why is it illegal?
We don't have organics on high school campuses.
Because they can explode them.
Well, very few organics. We have like alcohols and stuff, but nothing much.
But like, what is the what can they do that they won't?
Oh, they're nasty. They can be carcinogenic in nature, and yeah.
Are they the ones that if you drop it, like the biohazard team has to come and stuff? Like in the movie?
Not for these, but you're getting on the right track. All right, so you're looking at solubility here, and what I really want you to see here are the ion dipole forces that form, and they very often ask you to draw this, but a little bit easier Instead of drawing water molecules out, they have you draw little Mickey Mouses, which is fine. The only thing missing here are the lone pairs on the oxygen, so you would want to show those, as I'm sure you did on your quiz. All right. So potassium permanganate, potassium ion, and permanganate ion. There's the ion component. Then you've got a water molecule, and what you are drawing here are ion dipole interactions between the partial negative of oxygen and the positively charged potassium. Usually get 4 to 6 water molecules forming around, and they'll tell you how many to make. Usually they only have you draw 4. The permanganate ion shown here, and again the partial positive on the hydrogen, and you get an ion dipole interaction. And you'll see that this ion dipole force is very, very strong, and it compensates for the energy required to expand the solute and the solvent. The other way they very often have you draw it, I think, is actually easier, and I have seen this assessed on many, many AP exams in recent years. Let's say that you had sodium iodide, an ionic compound, sodium ion, iodide ion, and everybody of course knows the charges on the ions. And what they often give you is a Mickey Mouse structure representing your water molecule. So the big O is of course the oxygen, and the little ears on Mickey are the hydrogens. And they'll have you draw this, and I can't imagine anybody at this level messing this up. So here's our Mickeys. And again, the oxygen points inward. You form an ion dipole force. And that's a very strong IMF. Stronger than a dip to dip, stronger than a hydrogen bond. So what would be different for iodide ion?
The hydrogens.
Yeah, so now the ears, the hydrogens are going to go inward. And I can't think of a more perfect diagram for Florida, because we go to Disney World all the time. The happiest, most expensive place on earth. Well, maybe not the most. Anyway, you have to be able to draw these. You have to be able to know what layer turns purple and why. Last piece of the day. You have your Mickey's drawn? Question?
Is it always going to turn purple?
No, that's a good question. In my particular example, yes, but they can do it any which way they want, and they might say when this dissolves in this substance, it turns this color. When it dissolves in this substance, it turns this color, and you might have just pay attention to what they give you. I think one year I did like blue and yellow, just so kids didn't always think things turned purple. And then actually you're going to see it's kind of funny how chemistry blends into art, but when we get to spectrophotometry or spectrometry more, you really have to look at complementary colors and color wheels. It's kind of interesting how one color reflects a certain color but absorbs differently. And you may or may not remember this from bio. If you took AP Bio, you'd be more apt to remember it, but you talk about photosystems and chlorophyll.
We're doing that right
We're doing that in green right now.
Okay, so leaves very often are green, right? Because chlorophyll reflects green light, but what color light does it absorb?
Red.
Red.
Oh.
Yeah, so it's this complementary color stuff. We'll get into that later in the year, though.
Brown chlorophyll absorbs green, and
absorb
Chlorophyll
blue.
absorbs blue.
Well, yeah, we do a lab later in the year with dichromate and which is orange in nature, but we're going to set it on a blue setting, and they're complementary. In any event, the last thing I wanted to mention, two quickies.
Dr. K, was that the thing you did before vortex?
Yeah. So elemental P4 is often stored underwater. How would you describe P4? Polar or nonpolar? Definitely nonpolar, LDFs only. It's typically stored underwater rather than in carbon disulfide. Carbon disulfide has a similar structure to carbon dioxide. Carbon disulfide is a nonpolar covalent molecule. Why would P4 be stored underwater?
Because it doesn't mix with it.
It doesn't mix with it, so it won't react with it. All right? And then those ion dipole forces we took a look at, and that's going to assist in the breakdown of crystal structures because those ion dipole forces are strong. And this will lessen the tendency for ions to reform their crystalline state. And when you have water molecules around those ions, you have a shell of hydration or a hydrated ion. And you will find that an ionic solid will be water soluble if those ion dipole forces are greater than the interionic forces. So this goes back to our solubility rules. All group 1 containing compounds are water soluble. Please don't write that group 1 elements are water soluble. Sodium metal does not dissolve in water. It reacts with it, but it doesn't dissolve. All group 1 containing compounds are water soluble. So in this case, any group 1 containing compound must have stronger ion dipole forces than interionic interactions. Decide whether liquid hexane or liquid methanol is the most appropriate substance for grease. Definitely hexane. They're both nonpolar covalent, and the LDFs that form between them will be stronger, if you will, or release more energy than the LDFs you need to break in each one.
Do we have to say releasing energy, or can we just say stronger?
You're going to see the energy piece next time, and you're going to need it. Potassium iodide is what type of substance? Ionic, and so that is going to be more likely to dissolve in liquid methanol. You're going to be able to get an ion dipole interaction. This is a polar covalent molecule. All right, and we'll get into forming liquids in those steps with energy being released next time. This picture right here has been on many AP exams, so we'll want to take a closer look at that. But I don't want to rush this, and for some of you, delta H is very new. So I'm going to highlight green right there, and we'll pick up with that and get into those studies. And then there's not all that much of the chapter. We'll finish next time. We'll work on the practice quiz so you fully understand it. We'll review and test next week. But you're going to see the link between IMFs in this chapter, so you have to have mastered IMFs.